All right, we have really one last topic before we start looking at applications of this stuff. We're going to talk about absolute extrema. So we've talked a little bit about local maximums and minimums. We've used the first derivative to find those using that first derivative test, filling out the sign chart. What we're going to do is talk a little bit more about some local extrema a little bit later in this video, but we want to focus on absolute extrema, an absolute max and an absolute min. So maybe I'll go ahead and I'll draw a picture of a graph just to make sure that we know what the heck we're talking about when we talk about an absolute maximum and an absolute minimum. So let's say we've got some sort of a function that looks like this. This graph has a bunch of local maximums and local minimums, but we remember that it doesn't actually have an absolute max or min because this thing goes off forever in both directions. So that can be a bit of an issue with some graphs. Now, if we draw the graph differently, maybe I'll change my picture. Something like this. There we go. Then we have two local maximums and one local minimum, and we can see very clearly that we have an absolute maximum because this is the highest point on the graph overall. There's a lot of different pictures of graphs that we can draw. We can draw stuff with asymptotes that look like this, and I'm going to pretend that that levels off. That's an absolute max, that's an absolute min, all that kind of stuff. Now, we can also have pictures of graphs that look like this. Well, maybe I'll leave that. We'll get to it in a little bit. But that's the general idea between absolute and local maximums and minimums. The absolute extrema are the actual highest points or the actual lowest points based on the y values on our whole graph. I want to talk about the extreme value theorem, which is a very important theorem. It's a really helpful thing. It's one of the big things in calculus. This says that if we have a function that's continuous on a closed interval, then we must have both maximum and minimum. On some of the other pictures that I was drawing, we only had one maximum and no absolute minimums because the graph went down forever, or maybe we had none or something like that. Here, if we have a continuous function on a closed interval, then we're guaranteed to get both the maximum and the minimum every single time. Let me show you what I mean by this. I'm not going to prove this or anything like that, but what I will do is just draw some pictures and kind of show you why we need each thing. So first I want to talk about why we need a function to be continuous. Let's try and think about what functions look like if they're not continuous. The most easy, obvious answer is when we have these big old vertical asymptotes. And it's probably pretty obvious to say why this is a problem for absolute maximums and minimums, right? If the function goes up forever on this vertical asymptote or down forever, then of course it can't have both maximums and minimums here. So we need continuity because asymptotes could be problems. But also we might need continuity because we could have it go up to a point like this but have an open hole. And then we could look something like that. This doesn't have a vertical asymptote, but it is discontinuous. Here we can see that this has an absolute minimum. This point right here is the lowest point on our graph. But this one here is actually an open hole, meaning our function never actually gets up to it, but it keeps getting closer. This is a real strange thing, but technically we can keep finding points on our graph that are higher and higher and higher, and maybe we'd have to zoom in a bit more to see exactly how close we get. But this is almost like a limit, right? We keep approaching this hole without ever touching it, meaning the y values keep getting higher as we get closer. And so there is no biggest point on here because we can just keep getting a tiny, tiny, tiny bit closer to this hole, a tiny, tiny, tiny bit higher. So functions that aren't continuous have some problems. So we need continuous functions. And then it's probably pretty easy to tell why we need a closed interval. Let me just kind of show you what we do with the closed interval. Let's say we've got a nice continuous function like this. If I draw my little arrowheads on here, That's supposed to be an arrowhead. There we go. Then this obviously doesn't have an absolute maximum and an absolute minimum. But if I go back and I draw it again, but I cut it off and I say it starts at a closed interval and it ends, or at a closed point and it ends at a closed point, suddenly I don't have this end behavior that goes up forever. The end points here and here are our absolute maximums and absolute minimums. So we need a closed interval to make sure that we don't have that end behavior going off forever up or forever down, and we need it to be continuous, or else we could have things like asymptotes or those weird little holes. So that can be kind of an interesting thing. Anyways, for the extreme value theorem, we're going to look to see if we have continuous functions on closed intervals, and if we do, we know automatically that we get both the maximum and the minimum. So the question is, if we know that they're both there, what then? The extreme value theorem doesn't tell us where they are, how to find them, or anything like that. So we have like a little lemma, this is called. A lemma is like an addition to a theorem. It's like a little result that you can prove because of it. Now, I don't really like calling this one a lemma because it's not really based exactly on the extreme value theorem, but it is a small result. So this is something that's kind of a cool thing to keep in mind. If there are absolute extrema, if they exist, they have to occur at critical points or endpoints of a closed interval. Those are the only options. It's pretty easy to tell. We can just basically draw some stuff, right? If I draw something like this, I don't want to make it go off forever, sorry. I'll go closed interval here, and I'm going to go close point here. Let me erase that little end. Notice that my absolute maximum is right here, and my absolute minimum is right here. For this one, no derivative, sharp corner. That means it's a critical point. The derivative doesn't exist. For this one, horizontal tangent line, the derivative is equal to 0. Critical point. If we draw a different picture, then we've got our minimum showing up at a critical point because we've got a horizontal tangent line, but our maximum showing up at an endpoint. So basically, if they're not at critical points, then they have to be at like the ending point because it was going to go up forever or down forever, and we cut it off. So that's really it. So we only have these two options. They either have to be at critical points or they have to be at ending points. Now, what this is it makes it really easy to find absolute extrema, especially if we can guarantee that they exist. So we're going to do this in two different kind of steps. We're going to do the extreme value theorem to guarantee that they exist, and then after that, we're going to look at the critical points and the ending points, and we'll just have to see what we can see. So here's our example. This is a function. We want to find the absolute maximum and minimum on this closed interval. So, closed interval, that's good. Interval, there we go. What we need to do is check and see if this is continuous. This is a continuous function because we know that any polynomial is continuous. So, continuous function on a closed interval, that means that both of these things exist. That's good news for us. So we're going to use that little locating absolute extrema result that says we just have to look at critical points or ending points of our closed interval. So let's go find the critical points. We'll do this in our normal way. Find the derivative. 3x squared plus 6x minus 9. I feel like we've done this one before. Factor out 3. Now I've got to find numbers that multiply to get negative 3 and add to get positive 2. That's going to be 3 and negative 1. So that's my derivative. That means my partition numbers are negative 3 and 1. And we can go back and say, since our function is continuous everywhere, that means these are in the domain. So both are critical. So we've got all of our options. Our options, oof, that's brutal. Let me use a straight line. Our options for absolute maximums and minimums are pretty easy to find because they are the critical numbers or the closed endpoints. So we've got negative 6 for our closed endpoint. Negative 3, that's a critical number. 1, that's a critical number. And 4, that's our other closed endpoint. And all we need to do is see which one of these is going to give us the absolute maximum or the absolute minimum. We can do that by just looking at the y values. The way that we do that is by plugging these into our function. So we'll find f of -6 and f of -3 and f of 1 and f of 4. So take a second, see if you can find all these y values, and then we'll just compare them and figure out which one is going to be the absolute maximum and which one is the absolute minimum. Hopefully this is what you found. So what we can do is just compare the y values and notice that this one here is the smallest. So that means our absolute min is -6, -61. And our absolute max is at 4,69. Now, a lot of times we'll just refer to these by the y values. So we'll say the absolute minimum is -61 and the absolute maximum is +69. We'll just look at the heights of these things. The reason that we do that is that just in case there's a tie, every now and then we might have two critical numbers that have the same y value. Maybe they're both at +69 or something like that. And so we can just refer to the y value. That way there's only one absolute biggest y value. Because we really just care about what the absolute maximum height of our function is. We don't really care what x value it's at. So either give me the y value or give me the whole point. Now, the only real trick here is that it's possible that your critical points maybe show up outside of the interval. So what we're going to do is notice that this interval is essentially going to be the domain. That means when you get a critical point like -9, you'll look at this interval and say -9 is not in this interval, meaning it's not actually critical. It's not one that we're going to care about. So we only care about the ones in that interval. If I change that interval from 0 to 4, then suddenly we don't care about -3 because it wouldn't be in the interval from 0 to 4. That's really the only problem that we can run into here. We just have to be careful about that. So the extreme value theorem is really nice. As long as we have continuous function on a closed interval, everything works out pretty easily, and we can literally just compare heights of our points using a little table of values. Notice again, we're putting this into our function f, the original function, because we're trying to look at the heights of all these things. So what happens when we don't have a closed interval? Every now and then people can say, well, what about if it's not continuous? That ends up being a trickier problem than what we might expect. So we're just going to focus on the not closed interval. What if our interval is open? What if we're looking at -infinity to infinity, the whole real number line? Or maybe what if we're just looking at 0 to infinity or something like that? What if we don't have those closed endpoints? There's a theorem that we could write up and explain and all this stuff, but I figure let me just draw some pictures and show you guys what I mean here. Anytime we get lucky and we have one single critical point on an interval, something nice happens. So what I want us to do is to draw some pictures of a function with a single critical point. Let's say here's my critical point. And I'm going to make this critical point a local, I don't know, what do you want to make it? A local max? Let's start with local max. Let's say it goes up like this. I'm going to continue drawing my graph on the outsides, and I'm going to see what kinds of pictures I can make while making sure that I don't draw any more critical points. Really what I'm going to do is I'm going to see if I can make this point not the absolute maximum. Can I get my graph higher than that if I only have one critical number? Well, let me keep drawing it out this way, and I can kind of level off and start going up. But now suddenly you realize, wait a second, when you leveled off, horizontal tangent line, critical point. So maybe we'll say, all right, I'll just start jumping up this way. But suddenly you've got a sharp corner. Derivative doesn't exist. Critical point. So then we can say, well, what if we just made it not continuous? So if your function is continuous on an open interval, then we get rid of this problem, and suddenly we can't really make our graph get higher than this height here without turning it around. Those points that we turn it around are spots where we have horizontal tangent lines or sharp corners. So if we have an absolute or a local maximum and it's a single critical point, it's the only critical point, then it has to be the absolute maximum. So let me just write it out this way. Maybe I'll type it because my handwriting on this isn't great. If we only have one critical point on an interval, and I'll say the function is continuous, then if it's a local max, what that means is that it's an absolute max. And if it's a local min, we're going to find the same thing. Oops. It's an absolute minimum. Let me draw the minimum version of this. It's the exact same thing. I want to change this back to drawing, and here we go. So if I draw the minimum version of this, maybe I'll do a sharp corner minimum there. Then I won't be able to bring my graph lower than that without breaking the derivative or drawing another critical point by having a horizontal tangent line. So the only way that I can get back below this is by introducing another critical point. So that means if we get lucky and we only have one critical point on an interval, and the nice thing about here is that it can be open, then we just have to check and see if it's a local maximum or a local minimum. We have a test to do that. The first derivative test will do that. But what I want to do is introduce another test to do that, to find if it's a local maximum or local minimum. And then we'll use that for a couple of examples just to see what's going on. So this is called the second derivative test. Every now and then people get confused because the second derivative test sounds like it should be the sign chart that we do to check and see if a function is concave up or concave down and to find inflection points. Because the first derivative test is the sign chart for the first derivative. And so the second derivative test, people say, should be the sign chart for the second derivative. But keep in mind, this is the second derivative test for local extrema. We're finding local maximums and local minimums. The second derivative sign chart finds inflection points. Those are very different things. So here we go. Let's say that c is a critical number such that the derivative is equal to 0, meaning we've got horizontal tangent lines. What this means is that if our function is concave down, then we'll be able to tell something about what's going on. If our function is concave up, oh, I've got that backwards. If it's concave up, I read the inequality wrong. If the second derivative is positive, then we'll be able to tell something. And if it's concave down, the second derivative is negative, we'll be able to tell something. So what I want to do is, again, just draw some pictures. So I'm going to draw a nice little horizontal tangent line right here. And I'm going to go back and I'm going to draw a picture of a graph. Here's my critical point. It's one with a horizontal tangent line. So when I draw my graph, I have to level off and go flat here. So this doesn't work with sharp corners. But if I do level off and go flat, I'm going to draw it with it being concave up first. It's going to look something like that. Notice that this is a minimum. Similarly, if I draw another tangent line like this, and I decide to make my function concave down, then suddenly what happens is, here's my point, and if I make it downwards in its concavity, then this becomes a maximum. There's no other ways of drawing these other than stretching some stuff, I guess. But either way, it's always going to be a minimum or a maximum in these two cases. So if the derivative is positive, concave up, that means our point is sitting at the bottom, and so this is a local min. Now really, when we refer to this, we would think of like f of c, I guess, the y value, whatever. Similarly, if our function is concave down, if the second derivative is negative, then we've got a local max. And again, that's at the y value, f of c. The problem is when the second derivative is equal to 0. What this means is that there's like no curvature. It goes flat for a little bit, and flatter than just having a horizontal tangent line. So we have lots of options for what this could look like. The one that people think of a lot is if we had this point as an inflection point as well, meaning it could look something like this. And then we can say, oh, look, it's neither of those things. It's not a maximum or a minimum. What's weird is that it's possible that it could be a maximum or a minimum. Let me get rid of that one, and I'll draw a different picture here. And I'm going to really exaggerate this. Something like that. This point is technically a local minimum, but it's so flat in the middle that the second derivative is equal to 0. If you want an example of this, look at this function. Y equals x to the 4. Find the second derivative at 0. And you'll notice that the second derivative is 0 here. Find the first derivative at 0, and you'll find out that it's a critical point. So we've got a critical point. The second derivative is 0. It looks weird, but it is a local minimum. So basically, what happens is we don't know anything. A frustrating result of the second derivative test. If the second derivative is equal to 0 at the point we're looking at, then our test fails. Not because it tells us that we don't have a critical point or that our point isn't actually a maximum or minimum or anything weird like that. It just doesn't tell us anything. And so we have to go back to the first derivative test. So people will ask sometimes about this test, and they'll think, wait a second. If this test sometimes just doesn't tell us any information, then why would we ever use it? The first derivative test always works. The first derivative test will always tell us what we need to know. And so why wouldn't we do that? There's a couple of reasons. And mainly, it's that the second derivative test can be really easy to do in some cases. Some functions, it's way easier to just find the second derivative and plug in some critical points as opposed to building your whole sign chart, plugging in all these test values into the first derivative. If the second derivative is hard to find, then maybe using the second derivative test isn't a very great idea if you've got the option. So on these next two, I'm going to use this one critical point on an interval thing, and we're going to use the second derivative test just to get practice with it, to see if we can find some absolute maximums and minimums. So here's a function. Notice that the domain of this is from 0 to infinity. Because we've got this natural log, it doesn't take in negatives. So this function exists on an open interval, 0 to infinity. Let's see if we can find any absolute extrema. Since we have an open interval, we know the extreme value theorem won't work, even though this function is continuous on our open interval. So it's not closed, so extreme value theorem does not guarantee that we're going to get both of them. So we'll see if we can get one. What we're going to do is we're going to look for critical points, find the derivative. That's going to be 5 over x minus 1. And if we can find critical points, then we'll go ahead and try and see if there's only one of them. So we're hoping to get lucky and only get one critical point. What we'll notice is that there's kind of two right off the bat. At least there's two partition numbers. The first is 0, because if you plug 0 into this, your derivative doesn't exist. The second is 5, because if you plug 5 into this, you get 5 over 5. That's 1 minus 1. That's 0. So with this one, the derivative doesn't exist. With this one, the derivative is equal to 0. So when we talk about critical numbers, we got to check our domain. And luckily, we don't include 0, so that means this one's out. So we do only have a single critical number. That's good. What that means is that if this x value of 5, if we use the first derivative test or the second derivative test and it represents a local maximum, then it's the absolute maximum of this function. And if it's a local minimum, then it's the absolute minimum, because there's only one of them. So we don't have any more turning points where our function can loop back around and get higher or lower or whatever. So I'm going to use the second derivative test for this, meaning I need the second derivative. I'm going to rewrite this as 5x to the negative 1 minus 1. Our second derivative is negative 5x to the negative 2, or negative 5 over x squared. You know what's cool about this? I can tell exactly what's going to happen without actually plugging anything in. The second derivative test, if we go back, says that we have to evaluate the second derivative at the critical point and then check the sign of it. But here, I can see no matter what, this bottom part, maybe I'll do this in a different color. We'll just notice that this bottom part is always positive. If you put any x value in here other than 0, but we're not allowed to put 0 in because it's not in our domain, and notice we're only putting positive numbers in anyways. If you put any x value in here and square it, let alone the positive ones, you're going to get positive. Then you've got negative over a positive. This is going to be negative. Let's just double check it to make sure. F double prime of 5 is negative 5 over 25. Sure enough, it's negative 1/5. But all we care about is that it's negative, meaning our function is concave down. So this is what it kind of looks like here. We've got this horizontal tangent line. There's our critical point. Our function is concave down. So that is a local max. So it also has to be the absolute max. So if we want to find the absolute maximum, it occurs at the x value of 5. So the x value is 5, and the y value is f of 5, which is 5 times the natural log of 5 minus 5. I don't know what that is. If you use this in a calculator, you'll get some decimal or whatever, but whatever. That is the biggest y value that you can get on here. So that's kind of cool. We can use that second derivative test pretty well. Again, you could go back and confirm this using the first derivative test if you'd like, but I just want to use the second derivative test to get used to it. Try this one out. Pause the video for a bit. See if you can find your critical points. Hopefully there'll only be one. And then check out what's going on with the second derivative, and hopefully things work out pretty well. All right, let me just run through this really quickly so you can check your answers before we go. Our derivative is going to be 1 minus 4 over x squared, because you guys rewrote this as 4x to the negative 1. And that means that you've got some critical points. The partition numbers, we'll see. Partition numbers, you're going to find as plus or minus 2 and 0. If you put in 2, you get 2 squared, that's 4. 1 minus 4 over 4 is 0. If you put in negative 2, you also get 4, though. And then notice our function doesn't exist at 0. So here, we'll look at our interval, and for the critical numbers then, we're only going to be getting 2. Negative 2 goes away because it's not in this interval. 0 goes away because it's not in this interval. So again, single critical point on an open interval. Let's take a look and see what's going on. So second derivative test. We need the second derivative, which is going to be 8 over x cubed, I believe, because this is 1 minus 4x to the negative 2. So if we bring the negative 2 out, we get positive 8. X to the negative 3 looks like this. Cool. So we need to go ahead and check out what's happening at 2. 8 over 8 is 1. That's positive, meaning our function is concave up there. Critical point, horizontal tangent line, concave up. That is a minimum. So what we can say is that f of 2, which is 2 plus 4 over 2, which is 4, that is the absolute min. It's a local minimum, but because it's the only critical point, it has to be the absolute minimum because our function never has a chance of turning around and getting below it because the derivative would have to either not exist or be equal to 0. So the second derivative test is really helpful on these if it's used well. Now, in harder looking functions, it might be way more difficult to find the second derivative, in which case the first derivative test is just going to work just as nicely. I'll try in the next video that we do to kind of show you when the second derivative test is helpful, but we'll show you a bunch of different options on those things. For now, jump into these, try the second derivative test out, try and use it. It's helpful to go through and see what you prefer, what you understand. Don't just rely on the first derivative test for this stuff. Keep in mind that if you have a closed interval, we don't have to worry about this. We can just use that extreme value theorem that says it's guaranteed that both of them are going to exist. They're going to show up at endpoints of the interval or critical numbers. So build your little table of values and everything should be gravy. Good luck.